Hello and welcome to Monday Night Calculus. This is the last episode of this season. I am super excited to be hosting this once again. My name is Curtis Brown, and I'm joined again by Steve Kokoska and Tom Dick. I'm super excited to have you guys here this evening. We are going to be reviewing for the AP Calculus exam. And Steve, I think you've got a great qualification for getting us all ready for the exam, given your former chief reader status. I appreciate you offering your expertise and skills to let us know the kinds of things to watch out for and things to think about. So I'm going to turn it over to you and not take any more time.
All righty, I'm going to share my screen here, Curtis, get things set up. There we go. Hope that's working. I'm going to try one more thing here to make this just a little bit bigger. And here we go. Yeah, there we go. Beautiful. Well, thank you, Curtis, for arranging all of this. What we're going to do tonight is to review a little bit for the exam, which is coming up next week, 2 face-to-face versions and a digital version. Tom and I'm going to speak a little bit for Tom. We really don't like teaching or talking to the test, but I'm going to talk about some common errors tonight. And these common errors will lead us into a discussion, I think, of some content. And as usual, Curtis, I have lots of questions here tonight. And before I get going, we want to wish all of the students out there who are listening good luck as they take the exam. We hope you'll all score a 5. And to the teachers out there listening, we think that there are some good tips in here in this presentation tonight for your students. So here we go. I'm sorry this is sort of at the bottom of the screen, but I'm going to show you some common errors that I have collected over the years of being involved with AP Calculus. Believe it or not, some of these are very common errors for students, and I don't want you to make these. And again, these should lead into, I think, some content discussion. So here's the first one. Students out there, you should certainly recognize this as one of the definitions of the derivative, perhaps one of the most common ones. And a common error is for students to simplify this limit to the limit of this expression over here. And the reason that many students do this is because they take that f of x plus h and they write that as f of x plus f of h. You can't do that, although some students think you can. You cannot do that only under certain special circumstances. Don't make that mistake. Remember that what you need to do is to evaluate f at x plus h, evaluate f at x, and then do as much simplifying as you can, and then evaluate the limit. Now, if you're thinking about becoming a math major, here's sort of an open question. I don't expect an answer to this one tonight, but you might think about this one. Are there any functions so that that sort of an equality is true, so that you can write f of a plus b is equal to f of a plus f of b, where a and b are both non-zero? And I want to remind you, although I think of this as perhaps the most common definition of the derivative, remember, there is this, what I would call, alternate definition of the derivative. And we often see some questions on the multiple choice portion of the exam that are limits in this form, and students are asked to recognize that as the derivative of some function. So watch out for that. Watch out for that common error and that alternate form of the derivative. And here's a good one. This will lead us into a couple of, I think, good discussions. So if I want to take the derivative of the left-hand side, what's wrong with that? I'm just going to stare at that for a minute, let you think about that for 15 seconds, and see if you can see what's wrong with this. This is actually another very common error that students make under the pressure of a high-stakes exam. I hesitate to ask, but Curtis, do you see that error?
Hold on just a second. I just now got to the screen.
Okay.
So I think my screen is lagging just a little bit behind you, Steve. So
okay, well, that's a good reason. That's a good excuse, Curtis. Okay.
I don't know if it's an excuse, but it's a reason.
All right. Well, what has happened here is that the terms in the numerator have been reversed.
Yeah.
Okay. So in order to take the derivative of the left-hand side, indeed, you do have to use the quotient rule.
Right.
But you have to make sure that the terms in the numerator are indeed in the correct order. Now, there are some other notational issues that have come up recently here with this quotient rule, and I want to show you 2 of them. So let's take a look at this one first. If I want to take the derivative of the left-hand side, you would see that. and say, well, I've got to use the quotient rule. So I bring the denominator up, derivative of the numerator minus the numerator, derivative of the denominator. So that this numerator in this expression is correct. But the problem is in the denominator. Again, under the pressure of a high stakes exam that's timed here, students often forget this parentheses. The parentheses enclosing that x minus 2. And that's wrong. So we have to read that. Calculus readers have to score that as if it is x minus just 2 squared. Now, it's certainly possible that you might want to use this expression on something later on, and the student may correct that mistake. But in general, this will lose a point because that is bad notation. You know that on the new CED, we are stressing proper notation, so be careful of that one. And here's another one. Here's another expression. In order to take the derivative of this one, I need to use the quotient rule. And again, under a timed exam, this is a common error. There's some missing parentheses here. And if we don't see those parentheses, we think of this as just x squared times the cosine.
Right.
We think of this as just sine of x times 3x squared. There need to be this extra set here of parentheses in order for that expression to be correct.
Yeah, those grouping symbols are so important.
They are indeed very important. You'll see this, Curtis, come up a little bit later on when we talk about volume problems. Often there's lots of parentheses hanging around in those problems. Often they are calculator active. And making sure, you must make sure that those parentheses line up or are all there. Here's another one. Suppose f of x, capital F, is f of g of x. Then the derivative of capital F is just f prime times g of x. So what's wrong with that one? I hope there's a lot of hands going up. I hope there's something in the chat about this one, Curtis.
We'll put it out there to the chat. My screen is still way behind you. Okay. I haven't even seen the problem yet. So,
Tom, how's your screen? Are you seeing that pretty quickly?
And Tom's on mute. Tom's on mute.
Okay.
So he's not.
All right.
There you go.
So bottom of the screen, I'm seeing if capital F of x
Yes.
equals f of g of x. Yeah.
Is that pretty quick, Tom?
Yeah, it's been up there for a while for me. So
Okay.
they were experiencing different lag times.
Okay. So what's wrong with this one is the chain rule has not been applied. And so in order to take the derivative of capital F, you need to start at the outside, taking derivatives along the way and peeling away functions. So we take the derivative of the outside function f prime of the inner function. We need to multiply by g prime of x. Very common error here when there's a composite function. I'm just going to give you one quick example down here, and I'm actually, Curtis, if you'll allow me, I'm going to write another one in here. A couple of years ago, actually, on the BC exam, there was a question about arc length. And one of the functions in there was this one, I believe, f of x is equal to e to the 4x. And it was an arc length problem. So in order to do that, we needed to find the first derivative of f and then, of course, square it. That was part of the integrand, and there's a square root in there and so forth. But I would say that many students took the derivative of this function and just wrote it as e to the 4x because, well, the derivative of an exponential like that is just e to the stuff, but you got to multiply times the derivative of the inner function, which is 4. So a very easy composite function, but the chain rule was not applied correctly. So let's try to remember that for next week. Here's another common error. The sine inverse of x is equal to 1 divided by the sine of x. Sometimes students confuse that -1 up there with sort of a reciprocal. And that, of course, is not correct. This function right here is the arc sine of x. Now, I've noticed, and I don't know if this has been a conscious effort by ETS and the College Board, but I've noticed that we don't see this notation very often anymore. if they want us to work with, say, an inverse tangent or an inverse sine or cosine, this is the notation that they've been using recently. So you may recall from the exam last year, during the COVID year, or I beg your pardon, maybe even from the year before that, there was a limit that involved an arc tangent, and it was written like that, not with the -1 as sort of an exponent there. So don't make that mistake. And a couple little things down here too. I often get asked, well, should my students remember the derivative of the inverse sine? And my answer is, yeah, that might come up somewhere. There's often a question in the multiple choice portion that involves that. So yes, I'd remember that one. And I'm not sure why we always ask so many questions about this, but we often see a question about the derivative of an inverse function. And these questions often occur in a multiple choice question. And they often occur in the context of a one-to-one function so that we know it has an inverse. And it's a one-to-one function that may involve a transcendental and an algebraic, but you're told that it's one-to-one. And you're given the value of the function at a particular x value. And then you're asked to find the derivative of the inverse. And it can be done using this formula. Good, excellent. All right, how about a little particle motion here? Here's a common error. So a particle is moving along a straight line.
Yes.
Total distance traveled is the same as displacement. What's wrong
Only
with
if we're
that?
always going away.
What's that?
Only if we're always leaving or coming close.
Well, that's good. How about only if you're only going in the same direction? How about
There you
that?
go.
How about that?
Same direction.
Sure. Very good, Curtis. Excellent. Yeah. Total distance is not the same as displacement. So total distance traveled by a particle is really a scalar quantity, at least in my mind, the way that I think about it. It's the total ground covered. I often draw a funny diagram in my class. So total distance traveled is this distance plus this distance plus this one plus this one. All of that distance traveled all along a straight line. But what's displacement? Well, displacement, if I had a number line down here, is the distance from here to here. So total distance traveled is very different from displacement. How do you calculate those? You should know these formulas down pat. Often these kinds of questions occur in calculator active questions. Don't forget to set up the mathematical notation, the mathematical expression that leads you to your calculator answer. And I feel obligated to talk about one here down at the bottom. Let's just suppose in the context of a particle motion problem, you might have to find, let's see, the total distance traveled by a particle from -5 to 5. And that happens to be, let's say the velocity function. Let's suppose that this is not a calculator active question. How do you find this analytically? How do you find this without a calculator? What do you need to do? What's sort of the big picture here? The first step that you need to make in order to solve that problem. This is sort of I think this has become sort of a lost art because many of these questions are asked on the calculator active portion of the exam. But how do you solve that if you have to do it by hand with a piece of paper and a pencil? Any ideas on that one, Curtis?
I haven't seen anything in the chat.
All right, well, we'll leave that as an open question. That's a good one to work on, okay, as you're studying for this exam. How do you solve that? Definite integral may be related to a particle motion problem. How about this one? The particle changes direction whenever the velocity is 0. So, we're often given a velocity function or maybe a position function, and we're asked, well, find all the times when the particle changes direction over a certain time interval. Well, I'll just take the derivative. I'll find where the velocity is 0. Isn't that true? Isn't that all of the places, the values of t, where the particle changes direction? Is that true?
No.
Oh, good. Why not? Well, you knew it was in red, so okay.
Oh, well, I could stop and then continue going in the same direction for a moment, right?
That's very good. And so,
that would look like I don't know, probably a bad term for it would be a bounce, right? In my.
So thinking about the velocity function, what would have to happen in order to change direction?
I need to change signs.
Very good. The velocity function would have to change signs from positive to negative or negative to positive. Very good. Excellent. Excellent. The speed of the particle at a time t is the velocity. Common error. We see lots of free response questions where we're asked to find the speed of the particle, often asked to work with the speed of the particle. What's wrong with that one? Silence, huh? Sounds like my
sorry.
class.
I didn't mean to respond. I'm trying to read fast enough to catch up with you, Steve. Speed is the absolute value of velocity.
Very good.
So
speed is the absolute value of velocity.
We have an issue if our velocity happens to be negative there.
Very good. Excellent. So
I feel like I'm on a quiz show. have I won any prizes yet?
You're in the running. You're in the running for a new BMW 540.
Okay.
Yep, you're looking good. So one of the questions we often see in a particle motion problem, especially on the free response, is when is the particle speeding up or slowing down? Or more specifically, here's a time t. Is the particle speeding up or slowing down at that time t? Well, all right, to save a little bit of time, what we need to do is we need to take a look at the velocity and the acceleration at that time t. If the velocity and the acceleration are the same sign, then it's speeding up. If they are different signs, then it's slowing down. So I'm just going to scribble a little bit here, Curtis, down at the bottom.
Yes.
Okay. So let's suppose the time given to me, let's call it t sub 0 or t sub 1. How about that? So I'm going to look at a of t sub 1, and I'm going to look at v of t sub 1. And let's suppose that this is a calculator active question. I think the natural reflex reaction here is to plug these values into your calculator and write down an answer here. You have to be careful when you do that, because if you write an answer, it must be correct to 3 decimal places, up to 3 decimal places. And if it's wrong in any one of those, then you will not get credit for your answer. And so the best or the safest thing to do if it doesn't ask you for these values is to use your calculator and note, well, this one's greater than 0 and that one's greater than 0. So, okay, because that's true, the particle is speeding up. Now, there's another sneaky way to do this if it happens to be a calculator active question. I don't know, Tom may address this a little bit later on. I actually just not discovered this, but saw a student do this, and I thought it was very clever. If we are indeed given the velocity function, you can actually, on your calculator, you can actually compute the derivative with respect to t of the absolute value of the velocity, which is, in words, finding the derivative of the speed. And so if it turns out to be positive, it's speeding up. If it turns out to be negative, it's slowing down, and it's very clever. And it avoids all of this issue right here.
That's actually really shrewd.
Isn't that clever?
That is. I'm impressed. I don't know who that student was, but that's an impressive piece. I do have a comment that came in a little bit ago, Steve, on the question you were asking me to the definite integral that came in. Says Michael Carson says this: since it's even, you can double the interval from 0 to 5. But I thought you had an absolute value around that.
There is an absolute value around that, but it's still.
I mean, it's still
even.
Even.
That's clever, but I don't think it gets rid of the absolute value symbols. And so, what do you do after that?
Right.
And I'll tell you what. To make it to avoid the evenness, I'll make that -7.
Oh, so now you're just changing the problem on us.
Yes, I know. That's right. But tell Michael he's in the running for the car too.
Okay.
Okay.
Side note, there is no car surprise on this session. I just want to be really clear before I get TI legal shouting at me.
All right, we often see questions about the mean value theorem on the exam, and a common error that students make is that the value of C that satisfies the MVT is always the midpoint of that interval. Okay, it could be the midpoint, but in general, of course, it isn't. Here's some illustrations of the mean value theorem. In the one on the left, it might look like C is the midpoint of A and B, but not necessarily. Remember that we're just searching for this point C where the slope of the tangent line is the same as the line segment that connects A and B. The mean value theorem guarantees, it's an existence theorem, it guarantees that there is such a C. I always hated this when I was in school, but it doesn't tell you where it is. You got to go find it. Okay? So don't make that mistake. Here's a good one. If C is a critical number, oh, wait a minute, darn it, what's a critical number?
Steve, there's a follow-up to that other one up there. What are some functions where C is, in fact, the midpoint? I can think of one, maybe.
Well, there's a couple of easy ones I think you can do. What if f of A and f of B were equal and you had a nice parabola in there?
Parabola would be nice, yeah.
Be nice, yeah. Tom will back me up on this, but I don't know if I can classify or give you a classification of all functions for which that's true, because I suspect I can draw all kinds where I can get a value of C right in the middle.
Right.
So that's an excellent question. But I don't think there's just one class of functions like trigonometric or algebraic polynomial. It's a very good question. I think you were just avoiding this one. What's a critical number?
Perhaps.
Critical number, remember, is a number C. Oops, so that f prime of C is equal to 0, or f prime of C, I say D and E does not exist. So if I find a critical number,
value, okay, yeah.
Then son of a gun, C must have a local maximum or local minimum at C. Is that true? It's a candidate. It is what I call a candidate for a local extreme value. Remember that we still need to check whether f prime changes sign across that critical number in order to determine if it is indeed a local extreme value, or a local extreme value occurs at C. I'm just going to briefly mention a couple of things here in my notes. I'm going to look at sign charts first. I just want to remind you once again that sign charts are certainly okay to use, but they are not sufficient justification. I still encourage all of my students to use sign charts, but remember, in order to provide sufficient justification on the exam, you must interpret that sign chart. You have to give me a sentence or two that interprets that sign chart. The second note here is we always argue about whether or not the endpoints are included in intervals in which a function is increasing or decreasing. I think we've gone through this once or twice before, Curtis. I do indeed include them, but don't worry about it on the exam. As long as there is no contradiction. In other words, if we ask you where a function is increasing or decreasing, and you tell me the function is increasing from 0 to 5 like that, but the function is not defined at 0, then that would be wrong.
Sure.
So, okay, I guess if you're teaching to the test or you're looking at special tips for the test, always make them open.
Yeah.
All right, how about
here,
this?
Steve?
What's that? Go ahead. Go ahead.
It has to do with what you just had up there about critical values.
Sure.
Right.
And this is an error I've run into with students sometimes is for C to be a critical number, it does have to be in the domain of your original function.
Correct.
Now, the reason I make a big deal out of that is the critical value, f prime of C doesn't exist, but f of C has to. Okay. So, for example, if C is the location of an vertical asymptote, that doesn't make it a critical value because the function's not even existing there. So.
Right.
Yep. Good point.
Okay.
Okay. All right. Similarly here, Curtis, if f double prime of A is equal to 0 or f double prime of A doesn't exist, then f has an inflection point at A. Well, that's not true. That makes a candidate. I used to call these nominees. They are candidates for inflection points. And we still need to see if F double prime changes sign from positive to negative or vice versa. What about the endpoints here? Don't worry about them. As long as you have not included an endpoint where the function is undefined, I think you're okay here. Lots of problems on the free response portion of the exam here. We're often given a graph in this type of a problem. Remember, another way to think about concavity is whether F prime is increasing or decreasing. So make sure you can connect all of these things about concavity and inflection points with F prime. Okay, if F double prime of C is greater than 0, let me see, just think about that for a minute, then F has a local minimum. If F double prime of C is greater than 0, that means that the graph of F is concave up at that point. So that means F must have a local minimum at C. What's missing there? That's wrong. And the reason is because you have to make sure first that F prime of C is equal to 0 or does not exist. You've got to make sure that that derivative at C is equal to 0. This error occurred a lot in a problem a couple of years ago, one in which students were given their derivative in terms of X and Y. And they were asked to determine if there was a local minimum or maximum or neither at this particular point. And many students just took a look at the second derivative and plugged in and drew a conclusion and forgot to check whether the derivative was 0 there. So don't forget that one. This one is subtle. This is very subtle. It says if F prime of X is greater than 0 for X less than 0, F prime of X is less than 0 for X greater than 0. Let's see. So that means what? The function is increasing. Yep, X greater than C. Thank you. It's increasing and then decreasing. Then F has an absolute maximum value. F of C is the absolute maximum value of F. You won't get credit for that justification on the AP exam. Curtis, any chance you see what's wrong there?
Well, you're claiming a global maximum and you don't have evidence of that, right? There's
very good. Excellent. Yeah, there's a missing word in here and here. And it is the word all. Written like this, it is a local argument and you will not receive points for the justification. This often arises in the context of a problem where we're looking for an absolute max or minimum value on a closed interval. And there's only one critical value. And students will say, oh, well, this is where the absolute max is, and this is true. They'll write it like this. But written like this, it's a local argument and a global one. Very good. Excellent, Curtis.
See, I'm going to get that prize yet.
It's down to a t-shirt now, I think, Curtis. All right. In applying L'Hopital's rule, we take the derivative of the quotient using the quotient rule. Now, I think there's probably a couple people laughing out there at this one, but of course that's wrong. We don't use the quotient rule. We take the derivative of the numerator, we take the derivative of the denominator separately, and then we try to evaluate the limit. But I want to remind you of a couple of notational issues here. I apologize for this, Curtis. I'm going to write something up here on the screen, but then I'm going to erase it kind of quickly or scribble it out. If you're evaluating this limit, and you can see, let's say by direct substitution, because the functions f and g are continuous, you can see that this is equal to 0 over 0. Don't write that. You cannot write equals 0 over 0 anymore. That is improper notation here on the AP exam. Now, Tom and Curtis, you know I disagree with this, but for now, that is improper notation. You can't write that. So that begs the question, how do you demonstrate or convey that you're going to use L'Hopital's rule? Well, the best way to do it is to come off to the side and take a look at two separate limits and say, well, that one's 0 This one is 0, and therefore I have an indeterminate form of 0 over 0, and now I'm going to use L'Hopital. A little too wordy there, but the point is, take a look at those two limits separately. So there are some notational issues here. I think, at least in my mind, Curtis, the two most common notational errors I see are with L'Hopital's rule and, believe it or not, in applying the quotient rule. So when using the substitute, I'm sorry, go ahead.
Steve, we did have one question.
Sure.
Or comment, I guess, on the last one that we were talking about, the global maximum or minimum argument. And it could be in the wording that we have there. I just want to be sure. So the statement was made that f of c, we may not know if f of c exists.
Right. Well, there's a lot going on beforehand here. We know that
we need to talk about it being continuous, right? Or that it exists.
We have a nice continuous function on a closed interval. I'm going to apply the extreme value theorem.
Right.
We know there must be an absolute max and min in there, and the question asks for the absolute maximum value.
I wanted to be sure we clarified that, to be sure there.
Good point. Excellent point. Okay, here's a good one. When using the substitution rule, leave the antiderivative in terms of u. Okay, so I'm sorry, Curtis, I'm going to build a vision here. When I use the substitution rule, I use it because I start with a problem that's in the x world and it's difficult to solve there. And I build a bridge from the x world to the u world. My bridge is my equation that equates u to some function of x. And I drag everything across that bridge into the x world where I can, into the u world, where I can solve the problem, where it's easier. And what happens is that students will frequently leave the answer in the u world. So this is an example that I've done down at the bottom here. This is a pretty straightforward u substitution. And again, I do these a little bit differently than some people. This is me walking across that bridge. I'm sort of in the middle between the x and the u world. I define my function u, I find du, don't forget the dx on the end, and I always solve for dx in terms of du and x. I have the cosine of u, I have what dx is equal to, and I get some nice cancellation here. I'm on that bridge. I cancel everything out, and now I'm in the u world with a nice, easy integration by inspection. And what happens is that many students will stop right here, and of course you can't. The original problem was in the x world. You've got to get back into the x world, and how do you do that? You do that by looking at your original substitution here. So this is 1/4 times the sine of x to the 4th plus 2 plus c. Let me circle a little something here. We realize, we as mathematicians recognize that those two constants may indeed be different because one's in the u world, one's in the x world, but we're still allowed to use that same constant, capital C. Now, one more down at the bottom here. What happens if you change variables and it's a definite integral? So I want to remind you here that you should drag along the bounds here. And I know this will probably evoke a few chats here, Curtis. But now as I transfer, as I walk across that bridge from the x world to the u world, I'm going to drag along these bounds also. I have to write what the value of u, what value of u corresponds to this value of x. Now, I don't think I wrote this down here, but of course, u is equal to x squared plus 1. Now, somebody out there is already writing in the chat, well, why can't I just write x equal 3 and x equal 1 down there? Why do I have to do that? Well, what are you going to do in the next step? Now, everything in the integrand is in the u world. We don't want to leave this in terms of x because when I integrate this with respect to u, I'm going to plug in the u bounds. There's absolutely no reason to go back to the x world and then use the x bounds. And in fact, I would argue that that opens up more room for error. So when you drag the integrand over into the u world, drag along the bounds too. Okay, one other quick question here, Curtis, on this kind of a problem, and we'll leave this as sort of an open one. This is sort of I think this is kind of an easy one. What would happen if I made a substitution here and I simplified and I got something like this? This is a third problem, okay? 1/2 the integral, and I ended up with u cubed over x minus 1 du. So in other words, I dragged everything from the x world to the u world, and I'm thinking that I'm in the u world because I've got a differential over here du, but I'm stuck with that integrand that's got both u's and x's into it. What do you do in that case? That's a good question. We'll leave that for the chat. Hey, here's a common error. Usually, often on a calculator active problem, often where there are complicated functions given that cannot be symbolically integrated, or you can't find a symbolic antiderivative. This is not the difference squared. Remember, this is the washer method. It's got to be the outer radius squared minus the inner radius squared. Common mistake. Don't forget the pi. And one other tip here. Usually, or often in these questions, we're given named functions like f is equal to something, g is equal to something. Use the names of those functions, even if you're going about a horizontal line and not the x-axis, and the radius, the outer or the inner radius, is a little complicated. Use the name of the function. If you don't, there's more chance of a copy error, there's more chance of a missing parentheses. Oh, here's a good one. The average value of a function seems like it ought to be just f of a plus f of b divided by 2. That's kind of a statistical average, I guess. That's not true. And it's certainly not this. It's certainly not the difference quotient. Remember that the average value is this definite integral down here. This leads us to another common error, which I'm going to scribble just a little bit. Often what students will do is they'll say, oh, I know how to find the average value, and I'm going to start by finding this definite integral. The integral from a to b of f of x dx. And they'll work all the way down here, and they'll end up with, oh, I don't know, 72 over 15. And then they'll say, oh, well, wait a minute. I need to multiply by 1 over b minus a. So, okay, I'm going to write equal 1 over b minus a times 72 over 15. Well, that's a linkage error. These two expressions, this one and this one, are not equal, but they have been connected with an equal sign. And you will not get credit for that. That's improper. That's bad notation. Be careful of that. That's sort of this thinking, just thinking out loud or train of thought. This is universal logarithmic integration. I hope somebody's laughing about this one, but I'll tell you what, very common error. You can't do this unless you've got the derivative of the denominator in the numerator. And that leads to these two integrals. They're very similar. Jeepers, the only difference is that this one has an x in the numerator, this one's got a 1. How do you integrate? How do you find an antiderivative of each one of those? How do you do that? Gee, maybe that's another one we'll leave for the chat window.
Seems like these folks on the chat have an awful lot of homework here, Steve.
It seems that way, huh?
I'm looking for a couple of answers to come in and have somebody respond to those.
I hope your students are prepared for something like these two integrals right here. All right, improper integrals. Let's take a quick look at a couple of BC problems. BC
heads up, Steve. We're at about 39 minutes in. So
okay. Let me just do this one last one. I'll go to my last page and turn it over to Tom. So this is a common error with an improper integral. It seems reasonable to do something like this, to write this improper integral like that. But remember, our definition is you need to split this up into two separate improper integrals. So minus infinity to a of f of x dx plus the integral from a to infinity of f of x dx. A does not have to be 0, but often a equal to 0 makes that easier. And remember, one of these improper integrals like this is a two-step process. Make sure you find the antiderivative here and evaluate and simplify as much as you can, and then evaluate the limit. And often a L'Hopital's rule appears in here. All right, let me sneak to the bottom here and end with my final tips here. Remember to show all your work. Remember that bald answers frequently get full credit. A bald answer is just an answer where some supporting work is expected. I think Tom is actually going to address this issue of rounding intermediate results. Remember to store intermediate results to the greatest degree of accuracy allowed by the technology. If you can't solve part A, don't give up. Try to continue and solve B, C, and D. Don't waste time erasing bad solutions. If you've made an attempt at a problem and you say, wait a minute, I know that's wrong, just cross it out and move on. We won't read crossed out work. Darn it, make sure you answer the question. It doesn't have to be boxed or with stars next to it or anything, but make sure the answer is there. Don't say too much. I know that we have some great AP Calculus students out there, and some of them want to tell us a lot that they know. Look, just answer the question as succinctly as you can. Sometimes if you go to say too much, you'll lose some credit. Don't simplify a numerical answer, even if it's something like this. Sine of 0 plus 0 cubed over 64 plus e to the 0. No need to simplify that. It is a final numerical answer. Set your calculator to radian mode. Darn it, we still get students making that mistake. And I'll remind you that we do understand some abbreviations. We know MVT, we know IVT, but a common one that we don't know is M is not the universal symbol for slope. Don't make that mistake, okay? Use dy dx, but don't just write M is equal to 4 and expect us to know that that's the slope of a tangent line. All right, thank you, Curtis, for indulging me in all of that. I really do enjoy that stuff. I'll stop sharing and I'll turn it over to Tom.
Before you stop, you already did. That's okay. Back. We had one comment on the question that we asked about how do you integrate those? How do you find an antiderivative? Inverse tangent and U substitution seems to be. I was going to suggest U substitution. I'll admit that, but I had not fully processed the inverse tangent piece. So thank you, Michael, for reminding me. These are not quite as fresh for me as they are for some.
All right. Thanks, Tom. Thanks, Curtis. All yours, Tom.
Okay. So I'm going to share a screen here. And what I'm going to start with is I'm going to mostly work with the TI-84 tonight, some tips for kind of best practices for using your calculator on the AP exam. And of course, we're talking about the part of the exam where you're actually allowed to use a calculator. It's not best practices to use it on the other part. So
yeah, let's be really careful there, Tom, before what we encourage. And just to be clear, you're going to spend your time talking about the Nspire or the 84?
The 84, and I'm just using the Nspire here to present a typical question that might appear, especially on the open calculator part of the exam. I think problems involving area and volume. That's not guaranteed, but often we'll see one of those types of problems on the open calculator part. And so I'm really using the Nspire just to illustrate what a question might look like. So here it says the region R shown to the right is bounded between the graphs of y equal f of x and y equal g of x, where we're given these two formulas for f of x and g of x. And so we can see these two curves. Looks like f of x. That graph looks like a parabola with its vertex up. And then this red curve, that's our g of x. And we can see that it does bound this region R that's shaded. We have a couple of intersection points, but it doesn't look like those intersection points are right on the integers or anything like that, but maybe they are nice values. We'll see. So part A says find the region of R. Part B says the region R is rotated about a line. horizontal line y equals 3, find the volume of that solid. Part C, you got another solid that's using the region R as a base, and we're getting some cross sections described. The cross sections perpendicular to the x-axis are squares. What's the volume of that solid? And D, if we get to it, I threw in a BC kind of question here, which is find the perimeter of that region, which would really mean finding
That's a good one.
Planes. So,
Yeah.
But I just wanted to use this to kind of illustrate some best practices using your calculator. And Steve has kind of mentioned some of these already, but what I'm going to do now is shift over. These are simple enough. I think I can remember these two functions. I'm going to shift over to the 84. So I'll do this maybe a little bit clunky. What I did was stop the share, and then I will switch platforms. Let's see, didn't quite do that right. Let me try that again. So it means I'll share. And let's see if this works. I'll let you guys give me a little feedback here.
That looks great.
Excellent.
Okay, so here I'm on my y equals menu, and I'm going to go ahead and enter those formulas for those two functions we were given. I think it was 2 plus x minus x squared was that parabola. And now the other one, I think it was just a cosine of 2 raised to the x power. Yeah, if my memory serves me correctly, I got those in there right. And now I'm going to go ahead and graph those. By the way, this is something I would do if I'm faced with a problem like this on the AP exam, is I would, even though they supplied me with a picture, I would go ahead and graph the two functions, because one of the things it would do for me is it would store those functions away as y1 and y2, and now I have reference to them. I can apply those. But now I'm looking at this graph, I'm thinking, well, this doesn't look like the graph they showed me. Something is wrong here. I don't know, Curtis, can you help me out?
Well, you had me suspicious for a moment there that you had made an unintentional error until I saw the smirk on your face, which led me to go and check the angle measure on your calculator.
Sometimes
and
you
I
have
see
to look
that you
this
are
up,
in degree mode.
The models now, I mean, it has degree up here. It's telling us, oh, we're in degree mode, and that's the culprit.
I was highly suspicious of your graph there.
Yeah, and that's a reason to be suspicious when you see a trig function looking really, really flat.
Mm-hmm.
Should raise a little red flag, and that may be correct, but you want to check your degree, your mode, make sure it's there. So I'm going to go back to my modes. And there, let's go down to the fourth line there and enter radians. And let me regraph. That's looking a lot
now we look
more
a little
like,
bit
in fact,
more.
we've got a bit more of the graphs than what was shown in the picture.
Hey, and we had another person shout out that your calculator was in degree mode.
Yes, excellent.
Radians, somebody else shouted out. See, Tom, he's not just picking on me. You're not just picking on me. I was wondering, you guys know tomorrow's my birthday. I was just figuring out that maybe you guys are just giving me grief because
that's right. We will make you tell us how old you are.
Well,
that
we can have that discussion at a later.
Myself feel very old.
There you go. Exactly. I don't think you want to play that game.
Okay, so let's tackle part A here. I think we were just supposed to find the area of this region that's between those two curves. And here's one of those best practices, and Steve kind of mentioned it, I believe, was what we'll need to get to our answer is we're going to need these two intersection points, because that's going to be our bounds of the integral that will form. But those would be what we'd call intermediary results. So I'm going to find those using the intersection feature on the calculator. And so I brought up the calculate menu, and I see number 5 down there is intersect. Okay, let's try that. It says first curve. Well, the first curve is that blue curve. So I'll say, yeah, let's do that. Second curve's the red curve. And now it wants me to move nearby where I think the intersection point is. So I'll move approximately to where it is. Hit enter. And now down here, you see that intersection point is given to several decimal places. And that's something I really don't want to round at this point to 3 decimal places, because that's not a final answer. That's a result I need in building my answer. Now, before I go to find that second intersection point, I'm going to go ahead and leave the graph. And you saw that X value for the intersection. I'm just going to pull up X. And notice that that value's there. There it is. In fact, it's being displayed to even more decimal places than we had before. And the very first thing I'm going to do is I'm going to take that value and store it into something I can refer to easily. I'll just call it, oops, I think I accidentally, let's see, just hit a wrong key here. We want alpha A. So I'm going to store that value and all that accuracy into A. Okay, now it's there safely. I'll go back to my graph. I'll pull up the calculate menu again. I'll do intersect, blue curve first, red curve next. But now I'm going to move over to that other intersection point nearby. It gives me to that in much better accuracy. But then again, I will quit from the graph. And the X value that's in there now is the latest one it found, which was that intersection X value. You can see we've got to, gosh, 8 or 9 decimal places. And I'm going to store that in alpha B. Now, A and B are just placeholders for those 2 numbers with all the accuracy the calculator was able to muster. And so when I want to find the area of that region, see, I want to do an integral. So let me pull up my math menu. I'll go down to FN int. And this is a recent enough 84 that has this pretty print notation. That's very nice. It's actually notating this like we would regular calculus notation. If you have a calculator, if you had this in classic mode, or you had an older calculator and it actually gave FN int, you want to keep in mind that you want to present the integral using regular notation on your test paper. Okay. All right, now I don't need to type in these numbers in all their detail. I can just, in fact, I would say on my test paper, A is equal to this, and write it out to those decimal places. B is equal to this, and then the people reading the test, they see the student has declared those values and labeled them. They can now refer to A and B in that way. So I can actually put alpha A as my lower limit, alpha B as my upper limit.
So Tom, while you're doing that, just to reiterate, so once I have computed those values and I have them stored in A and B on my calculator, I can declare them on my test paper, record them to the number of digits accuracy displayed there. Do I need to do just that number? Should I only include the first 3?
I would include them all.
Include them all? Okay.
Make it very clear to the person reading the test that you had actually calculated this out and had not done any intermediary rounding.
Okay. I just want to kind of make sure that we're being clear about that, because of recording the number of digits. Do I need to be careful of making a recording error there, is that going to be held against me later on if my answer is still correct, even though maybe I put down a 6976634 instead of
Right.
5634.
Yeah, that's the danger of if these numbers are used over and over again, as they are in this problem, and there are problems on the AP exam where intersection points like these might be used 2 or
Sure.
3 times in different parts of the problem. If I copy this number down in all those digits, it's just opening up opportunities for me to miscopy. And so
Sure.
getting those stored as soon as possible and declaring them on my test page is a good way to go.
So
Right.
Curtis, this raises a very good question. You know, on the AP exam, we talk about 3 digits to the right of the decimal. So many students have a tendency to write just 3 digits to the right of the decimal.
Right.
And what happens is they'll write A and B as that, 3 digits to the right of the decimal. And many of these problems are pretty, what's the right word, Tom? Robust. Yeah, just a little bit away, it's a little bit off, you still get the right answer. But the problem is we don't know whether or not the student has used 3 digits or they've actually just written 3 digits and stored it to the greatest accuracy of the machine.
Right.
I think that makes this kind of a problem very difficult to grade. That's just
Sure.
It can be, yeah. And that's why clearness of communication can really help out the student.
Absolutely. Absolutely.
This is why I was asking some of those questions, because I want to make sure that we're explicit about that information. Good.
And now, by the way, because I've got them in the calculator stored as Y1 and Y2, the 2 curves, notice I don't have to retype in their formulas either. I can just refer to them as Y1 and Y2. On the test, because these were named as f of x and g of x, by the same token, you could present on the test literally the integral from a to b, f of x minus g of x dx. And because those are declared on the test, they're labeled clearly, you can use them as reference. So that's a lot easier to write down the reference to the function than it is to write out that whole formula, because like Steve pointed out, the parentheses can be the bane of the student's existence. If you drop a parenthesis in the wrong place, you've changed the meaning entirely. Yeah. So I'm going to go ahead and enter this here. And to be honest, I don't know how robust this particular integral was. It could have been fairly robust, as Steve said, where if I had rounded these to 3 decimal places, maybe it would still be accurate enough, but really you're playing with fire if you do that. Don't round it intermediate results. Go with full accuracy here.
Absolutely.
I think,
and two more comments on this, and then Steve, go ahead.
Yeah. Sure.
So I did have one person write in asking, or maybe stating that the writing it down on my paper, recording it to the 3 decimal places and not, and then storing it on my calculator. There's a question about that. So I think we addressed that. The encouragement is write out all the decimal places. Because then you've worked on.
Then you're safe.
Second question was, or comment was, on the 84, Tom, I noticed that you put in y1 at x, or y1 of x and y2 of x dx. And in this case, do you need to use the x's? I think on the 84, you can get away with not doing that because it assumes those values, right?
Excellent point, Curtis. And thank you for, I was actually thinking about that as I was typing it in, was thinking that this is not necessary, but it's close
just good notation.
To the notation that we would want. And in fact, it's looking more like the f of x. In fact, here on the test, I really would want to use f of x and g of x.
Right.
And I wouldn't want to write just f minus g. I'm not sure they would take off for that. Steve might have a better handle, but you'd be walking on the edge there.
Yeah.
And you do need, just for clarification, the comment was also made that you would need this if you were doing this in Nspire. You would absolutely need the X.
Absolutely. Yeah.
You cannot just do F minus G on the Nspire.
Now, in fact, on part B here, I think we had a solid of, it was a volume of revolution. And so let's go ahead and do that. Let's see, that's going to have that pi involved. And I tell you what, I'll try to, I don't know if I should switch back to the Nspire to look at that problem, or
I think you can just tell us, remind us what it is, because we are kind of bumping up against the time slot. So, but I want you to go ahead.
I'll tell you what, I'm going to jump to part C.
Well, I'd like you to, I'd go ahead and answer them. I think that's a good idea to answer them. Just tell us what the problem was.
Okay, it was rotating the region around the line.
Y equals 3. Okay.
Yeah. So now that line is up above the region, so our outer radius is going to be the curve furthest away from that line, which happens to be the Y2. So I'm going to go ahead and put in our pieces here. Let's see, I think there's going to be a pi involved. So let's get pi. And then we'll multiply that by our integral. And again, we'll just go from alpha A to alpha B. It's really nice not have to type those in. They've been declared once and for all. And now my outer radius is going to be 3 minus our Y2. And I'll go ahead and leave off the of X here, even though we would want to include the function notation would be like g of x here.
Right.
So that was our outer radius squared, and then we'll subtract the square of our inner radius, which would be 3 minus for us, it would be the Y1.
And we're seeing in real time the grouping symbols and the importance of those grouping symbols that Steve was talking about earlier. How that square is going to come into play here.
Yeah. So this is 3 minus Y2 is my outer radius.
Squared, not cubed.
Oh, just checking.
Pi r squared.
That was that little birthday present for you there.
Pi r squared, not round.
And then we'll integrate with respect to x. Aha. Okay.
Yeah.
And one more point about this. It may sound like we're making a huge deal about this accuracy, but another place where this sometimes rears its head is students will do this integral. They'll get a decimal number for it, round it to 3 decimal places, and then multiply by pi. Again, that's risky. It could be, that's like an intermediate result. It's a multiple of pi, but this here has given me the full accuracy of that product. When I say full accuracy, as much accuracy as the calculator could report.
I think one thing we also saw, Tom, was some students who actually computed that definite integral and then wrote that answer. Let's say it's like 31 point something times pi is the final answer.
Yes. Yeah.
Right. So as long as that 31 point whatever it is, as long as that's correct, that would be okay, I think. Yeah.
Well, I think it's been on the line, Steve. I think
yes. Yeah. Correct.
Where they said, well, it's not quite
what we wanted.
Yeah.
Yeah.
So it's dangerous. I would say, go for that much accuracy you can. Also, there is no obligation to round or truncate this to 3 decimal places. I mean, I want to tell students that is, you could go ahead and write this out. The graders will check it to 3 decimal places, but if you have additional digits, there's no problem with that at all, really.
Yep.
So, to me, that's a way maybe to guard against accidentally rounding those intermediary results. So,
Right.
So I think I'm going to stop there, Curtis, because those other problems, just depending on how much time we had, by being able to refer to y1 and y2, where I have my function stored, and then refer to this a and b once I've calculated them very simply, this is not only more accurate and more efficient for me, it actually makes it easier on the readers. Folks grading the exam can follow your work very, very clearly when you make these kinds of these practices.
We like to make the readers happy.
Well, correct mathematics makes the readers happy. I'll say that. Okay.
Isn't that fun?
God. I'll go ahead and stop my share and turn it back over to you, Curtis.
Well, that's fantastic. Always a pleasure, Tom and Steve. I sure enjoyed this. We've had a lot of fun this year going through the calculus curriculum, the units, and looking at a variety of different things. And then this week, wrapping up with some test preparation. I do want to reiterate kind of the good luck and the well wishes to all the students out there who are going to be taking the exams over the next, next couple of weeks. Even there's several administrations depending on your situation. So we just want to wish you well and good luck on that. Steve and Tom and myself will be doing this again next year. So let your calculus teachers know that we will have another series of Monday night calculus. Not exactly sure what that's going to look like just yet, but we'll make announcements, and you can always be looking for those things on education.ti.com and on our social media platforms. At TI Calculators. Go ahead and look for us out there. Once again, I do want to appreciate and thank Caria and Allison and all of the folks at Texas Instruments who've helped us to put this on. We've really enjoyed having you, and certainly appreciate doing this. So for now, I'll sign off and wish you guys very well.
Thanks.
Good night.